It's actually pretty fun because like you're basically doing the job, you know. Yeah. What? Are you sick? People to replace some of our seniors. The paper, you know, chairs. Oh, that. It's uncomfortable. What? That was very uncomfortable. Oh, I really. But it's more like construction management. Is that what you're trying to do? Yeah. Basically doing the job, as you say. Instead of like months of time though, you have 1 day. I'm sorry, everyone that's going into construction management.
All right, hello, can you guys hear me on Zoom? Okay, cool. Sorry about that. Yeah, the microphone, there's like 2 microphones in this room, and which one actually works on any given day is like random. So I pick one and then hope it works, and then it's usually the other one. So yeah, just let me know beginning of Zoom if my mouth is moving, but no words are coming out. So okay, so what I was saying, so today we are going to be finishing up our lecture notes on second order ODEs. We have just one more, just a quick example I just want to set up for you guys with undetermined coefficients. Then we got to talk about resonance. Then moving on to something new. So, you know, up until this point in the class, I think probably for a lot of you, this class has been a lot of review, specifically from you know, Math 250B. But Laplace transforms is the point where this class kind of takes off into kind of its own direction. So you know, so far we've been going pretty fast with the ODE stuff, but for Laplace, you know, we're going to slow down a bit just because it's new stuff. And then, you know, you'll see its usefulness. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. Let's go and get started. And so where we left off last Thursday was this concept of undetermined coefficients. Hello, hello. Okay. The microphone breaks every now and then, so I'm hoping that it stays stable for the class. Okay. All right. So the method of undetermined coefficients. So this was a method that we learned how to do to solve for particular solutions to non-homogeneous second-order ODEs. Okay. All right. So just to kind of you know, remind you, so a second-order ODE looks like the following. So we have y double prime plus py prime plus qy, right? And then we had some function out here, r of x, okay? So in particular, you know, we were looking at ways to solve for solutions to this r of x function over here, right? Right, so that's what we mean by non-homogeneous problems. And so when we have a right-hand side that's not equal to 0, okay? And our general strategy with method of undetermined coefficients was to say that our particular solution, or the part of our solution that solves this part, should have the same functional form. Okay, so whatever form that right-hand side term is, we're going to guess a similar function. The only difference is that our similar function is going to have undetermined coefficients. Okay, so that was kind of the whole crux of the whole thing. So let's do an example. I'm not going to solve this example completely out just because of time. We are a bit behind just because I've been yapping for too much. But I'm going to show you at least how to set up the problem, and then, you know, I'll leave, you know, the rest of the example up to you guys. Okay. Okay. So for this example, we have y double prime plus 2y prime plus 0.75y. This is equal to 2 cosine of x minus 0.25 sine of x plus 0.09 x. Okay. All right, and so what we want to do is we want to find out, or we want to solve for the full solution to this problem. So that's homogeneous solution as well as particular solution, and then add them together. Okay. Okay. So with these kinds of problems, non-homogeneous, remember there is basically a three-step process that we follow to solve for its solution. Okay. All right, so let's review just very quickly what that process is, just because you're going to be doing it a lot in the homeworks, and just so you know the process. Okay, so step one is to solve what's called the homogeneous problem. Okay. So with the homogeneous problem, what we're going to do is we're going to set the right-hand side equal to 0 and solve it using the characteristic equation. Okay. All right, so basically for step one, we're going to neglect the fact that we have a particular solution for now. Solve for the homogeneous solution, because that's ultimately going to be part of our full solution at the end anyway. So you might as well solve it now. Okay, so the homogeneous problem here is y double prime plus 2y prime plus 0.75y is equal to 0. Okay. So I've temporarily kind of eliminated the right-hand side to this equation. Okay. So what we have is a second order linear ODE with constant coefficients, right? And so we know what to do in this situation. We are going to replace this with our characteristic solution, our characteristic equation, excuse me. So we have lambda squared plus 2 lambda plus 0.75 is equal to 0. Okay. And so we basically replaced our ODE with the quadratic equation. So let's use our quadratic formula to find the roots. Okay. All right, so our quadratic formula in this case is -2 plus or minus square root 2 squared minus 4 times 1 times 0.75. All divided by 2. Okay. And this is lambda 1, lambda 2 is equal to. Okay. All right. And so we do the math here. We have -2 divided by 2, that's -1, plus or minus square root. 2 squared is 4. 4 times 0.75 is 3. So we have 4 minus 3 square root, that's just 1. Okay. We have -1 plus or minus 1 over 2. So that means our roots here, you have lambda 1's equal to -1/2. And lambda 2 is equal to -3/2. Okay. Okay, so we have two real roots here. And so with two real roots, our homogeneous solution looks like the following. So we have YH of x is equal to C1 e to the minus x over 2 plus C2 e to the minus 3x divided by 2. Okay. So that's our homogeneous solution. So, we always solve the homogeneous problem first. First of all, it's usually the easier part. So usually it's, you can get this part pretty quickly. Especially if you're really good at finding roots to a quadratic formula or a quadratic equation. You don't have to use a quadratic formula, so this part becomes pretty simple. So we do it just based on that, but we also do it for another reason. The other reason we do this, remember from last time, is to make sure that our guess for our particular solution is linearly independent from our homogeneous solution. Okay, so that's the part that often gets skipped. And a lot of times when people skip right to the particular solution, sometimes they miss this fact, and their guess for their particular solution is incorrect. Okay? Okay. So remember that was kind of the last example we did last Thursday, where we had I think our homogeneous solution was like e to the minus 2x or something like that, and our guess for the particular solution would also be e to the minus 2x, but we can't have that, and so in order to make it different, remember we multiply by x to make it linearly independent. Okay, so that's kind of the main reason why we solve for the homogeneous solution first, is to make sure that our guess is sufficiently different. Okay. Okay, so then after you solve for the homogeneous solution, step 2 is to guess a form of the particular solution. Okay, based on the form of the non-homogeneous term. Okay. Problem 2. Okay, so the microphone. All right, the microphone's going crazy. Okay, let me write out our non-homogeneous term again. Okay. We have r of x for this problem is equal to 2 cosine of x minus 0.25 sine of x plus 0.09 x. Okay, so I wanted to do this example with you guys, not fully, but just to set it up, because this is a case where our non-homogeneous term actually has multiple different types of functions, and I wanted to make sure we go over that just to make sure you know how to deal with it. Okay. Okay. So let's look at this function here, and let's find out kind of which types of functions we need in our particular solution. Okay. So let's look at these two terms first. So we have 2 cosine x minus 0.25 sine of x. Okay. So these are sinusoids. More particularly, they are sinusoids with frequency 1. Okay. Remember, the frequency of a sinusoid is the coefficient inside the argument here. So since this is just cosine x and sine of x, that's basically the same thing as cosine of 1 times x and sine of 1 times x. So the frequencies of these is just 1. Okay. And that means our particular solution must also have sinusoids with frequency 1. Okay. So our guess for yp of x, right? So we're going to include both sinusoids, so both cosine and sine. Remember, no matter if the particular term had just one cosine or one sine, our particular solution has to include both. Okay. For this case, you know, our non-homogeneous term has both sine and cosine, but just know that you always have to include both in your guess. Okay. So right now our guess is a cosine of x plus b sine of x. Okay. Right. So A and B right now are undetermined coefficients, and so those we're going to determine after we solve this problem. But we at least need to guess the form. Okay. The other part of this non-homogeneous term is this. So we have 0.09x, and so this right here is a linear polynomial in x. Right. So it's a linear because, you know, x is only to the first power. Okay. There's no x squared or x cubed, so there's no quadratic or cubic terms. Okay. So in this case, our particular solution also has to include a linear polynomial, but it also has to include all the lower order terms as well, of which there's only one. Okay. And so to this, we're going to add two more terms, and so we're going to add cx. Okay. There's our linear polynomial, so we have some constant c times x. Okay. Now remember, when you're dealing with polynomials, you have to include all the lower order terms as well. And so we're going to add a plus d for the constant. Okay. Okay, so that's right here. That's our guess for our particular solution. There are 4 undetermined coefficients. Any questions on how we got those 4 terms in our guess? Okay. So that's the fun part. The fun part of this problem is coming up with the guess. The tedious part, or the not fun part, is actually solving for these coefficients. Okay. All right, question for the chat. Question. So even if we have multiple trig functions, we still just use a cosine plus b sine. Yes, correct. Now you have to be careful though. So if you have multiple trig functions that are different frequency, you need to include all terms of those frequencies. So actually, let me give you an example. Right. So this is an example within an example. Okay. So let's say your r of x is, 3 cosine of x plus 4 sine of 2x, right? So you actually have two different trig terms with 2 different sinusoids, or 2 different frequencies, excuse me. Right? So in this case, you have to actually account for both of these frequencies. So your yp is going to be a cosine of x plus b sine of x. Right? So this would be the guess that corresponds to this term here. Okay. But then you also need sinusoids that match the frequency of the other term as well. So you have c cosine of 2x plus d sine of 2x. And these two would correspond to these right here. Yeah. So it definitely gets messy when you have sinusoids or when you have trig terms of different frequencies. So just kind of make sure that you're kind of aware. Okay. For this class, I don't think I would give you something like this just because this is just kind of mean. But Just be aware of it if you do see it in the. Mhm. All right, any other questions on this? Okay. All right, so once you have your guess for YP, step 3 to these problems is to take its derivatives and then plug it back into the original equation. Okay. And so you're going to solve for YP prime, YP double prime. Okay. And you're going to plug these back in to the original ODE. Okay. But you want to make sure that you also include the non-homogeneous term as well. Okay. So just in the interest of time, just because I want to make sure we start Laplace transforms today. I'll let you kind of do this part here, but the problem's kind of set up for you. From here, it's mostly just taking derivatives and just working through the algebra to solve for A, B, C, and D. Okay. Okay. But if you did want to see the full solution, it is worked out in the notes. And so if you go to the lecture notes, kind of in the second half, I probably page 13, 14, or 15, I forget exactly. This exact example is actually worked out there, so you can find this in the lecture notes. So if you're curious, you can find it there. There's also a couple other examples that I didn't get to do, and so those are all in the lecture notes as well. Okay. Generally speaking, my lecture notes, I try to be as thorough with the lecture notes as possible. I may not have time to cover absolutely everything in the lecture notes, and so if you want to see more examples on the techniques that we're covering, I would definitely check out the lecture notes. And sometimes I have additional handouts with more examples as well. All right, any final questions on this before we move on to resonance? Okay. All right, so let's move on to resonance. So resonance is a very interesting phenomenon. It is something that is really very, very important for engineering, especially if you're doing any kind of structural design. So civil engineers, this can be very important. Mechanical engineers, this can be very important for you guys as well. Even for electrical engineers too, you can have resonance in an AC circuit as well. That you generally want to avoid. So let me start by saying resonance usually is a bad thing. You don't want resonance to occur. The reason resonance is a bad thing is that usually if resonance occurs, you're going to have some kind of system failure of some kind. And so this is particularly relevant in the realm of vibrations. And so when you're designing a structural system or a mechanical system, you always want to do vibration testing or resonance testing to make sure that your system is not going to resonate. Okay. And then for the electrical engineering application, AC circuits is something where this can happen as well. Okay. So I wanted to get that out of the way because resonance, a lot of times when you see it kind of described in kind of math textbooks, engineering textbooks, people usually describe it as something that's really cool. And it is something that's really cool and something that, that is kind of amazing kind of when you see it. But it's only kind of cool to look at. But if you're the engineer in charge of a project, it's usually not something that you want to see, right? So what is resonance? So resonance is basically a high amplitude oscillation or high amplitude vibration that occurs when a system is forced at its natural frequency. Okay. And so the operative word here is large amplitude. Okay. So it basically causes these vibrations that occur at very large amplitude, much higher than you would probably expect from the nature of the forcing or the nature of the forces involved. And so it basically aims to amplify these oscillations, usually up into a point where the system just either structurally fails or mechanically fails until something breaks, basically. Okay. Okay. So let me give you some examples of this occurring. Okay. So probably the most I guess striking example that's usually shown specifically to engineering students and engineering people is the Tacoma Narrows Bridge. Have you guys seen the Tacoma Narrows Bridge before? Have you kind of heard of it before? So Tacoma Narrows was this bridge. It was designed a long time ago. It was basically kind of a suspension bridge. Good. Yeah. So it was a suspension bridge that went over this kind of part of the region that was very windy. And this idea of resonance and this idea of vibration was still kind of the theory for this was still kind of being developed at the time. And even if the engineers knew, they kind of just largely ignored it in the design. And so what happens is as the wind kind of hit the bridge, it caused the bridge to vibrate at the exact frequency of the natural frequency of the bridge, which caused the whole bridge to kind of, do this kind of really crazy stuff. So if you haven't seen a video of the Tacoma Narrows Bridge, I would definitely, check it out. It is pretty amazing to look at. It's amazing to look at and just be glad that you weren't standing on the bridge. But that's probably the biggest one. Another one that you've probably seen is a party trick. Okay. And so you've probably seen videos of this, but it's possible to break a wine glass or to break a small glass just by singing. This is usually a trick that's done by opera singers, and so people with kind of a naturally kind of loud voice, someone that can control their voice at a particular frequency. But typically, what happens? It looks like this. So you have a wine glass, right? Right. And you have a person. Maybe they're upset or something, right? And so if they sing at the wine glass at a particular frequency, right? So sound waves are the way that we perceive sound waves. These are just basically just fluctuations of pressure within the air, right? And so every sound has a distinct frequency at which it travels, right? And so if the frequency of the singing voice is such that it matches the wine glass, it causes the wine glass to kind of vibrate so violently that it could just end up breaking. Okay. So that's kind of another situation of resonance occurring. Okay. Okay, and then you can come up with a lot more examples as well. So, the concept of, if you've been on a swing on a playground, and so the idea of, making yourself go much higher on the swing, that's resonance right there. So kicking your legs in tune with the natural frequency of the of the swing. Okay, so there's tons of examples. Let's see how it works out mathematically. Okay. So this idea of resonance is really timed well with our discussion of non-homogeneous terms. Okay. So when the non-homogeneous term in a second order ordinary differential equation matches that of the homogeneous solution, okay. So when the non-homogeneous term matches the same form of the homogeneous solution, that's when resonance can occur. Okay. Because remember, what happens when this occurs? So when this occurs, right, in order to make sure that our particular solution is mathematically different from the homogeneous solution, we have to multiply it by x. Okay. So let me give you an example, kind of a very kind of simple example that shows you how resonance can occur. Okay. So let's take this second order equation. So let's say we have y double prime plus 9y. Okay. Let's say that this is equal to cosine of 3x. Okay. So let's solve for the solution to this problem here. So let's go through our process here. So number one, we're going to solve for the homogeneous solution. So the homogeneous solution is y double prime plus 9y is equal to 0. Okay. If we do the characteristic equation here, we have lambda squared plus 9 is equal to 0. We see lambda is complex conjugates here. Lambda is plus or minus 3i. Okay. That means our homogeneous solution YH is a cosine of 3x plus b sine 3x. Okay. All right, it's pretty straightforward. Okay. Step two. Now let's consider the non-homogeneous term. So the non-homogeneous term right now is cosine of 3x from the problem, right? So let's make a guess for the form of yp. Okay. And we'll do it based on our form for r of x. Okay. So yp, it should be a sinusoid of the same frequency as the forcing term here. Okay. So let me call this c cosine of 3x plus d sine of 3x. Okay. Okay. But we have an issue here, right? And so if we look at the form for our particular solution, we see that it's exactly the same form as our homogeneous solution, right? So we can't have that, right? So our particular solution must be linearly independent from our homogeneous solution. And so what do we do in these situations? We multiply by x, right? So our guess for our particular solution will be cx cosine of 3x plus dx sine of 3x. Okay. Okay. And so of course the next step here would be to take its derivatives and plug it back in. But just in the interest of time, I'm not going to do that. But I am going to highlight this yp. Okay. And so eventually, our y of x, or our full solution, is going to be yh plus yp. Okay. So that's a cosine of 3x plus b sine of 3x plus cx cosine of 3x plus dx sine 3x. Okay. So let's look at this solution here. In particular, let's look at our particular solutions here. Okay. Cx cosine of 3x. All right, if you plot this, essentially what we have here is a cosine term with a frequency of 3, but its magnitude is going to be increasing according to x, right? So you can imagine as x gets bigger, so as x goes from 1 to 2 to 3 to 4 to 5, the magnitude of this cosine is going to start to amplify as x gets larger. Okay. And so if you plot it, it's going to look something like this. And so it may start kind of modest like this, but eventually, it's going to start getting bigger and bigger. Okay. Okay. And of course, this looks cool, right? So this is cool to see that the solution kind of grow like this. But again, this is usually not something that you want to see in your structural system, right? Because eventually, the magnitudes of the oscillations are going to get so big that your structure or your system cannot physically, sustain those large amplitudes. Okay? And so just like I mentioned before, eventually you're going to reach a point with resonance where your entire system just fails or breaks. Okay. Any questions on how this result was obtained here? Okay, good. Okay, so how did this occur, or what are some important points to highlight with resonance, right? Okay, so the thing to remember with resonance is that when you have a second order ODE, there's always going to be what's called a natural frequency of the system. So physical systems Physical systems whose behavior is governed by a second order ODE will have a natural frequency. So that natural frequency, you can think of it as the frequency at which it naturally likes to vibrate, okay? And so determining the natural frequency of an object is actually very simple, although it's a lot of times it's kind of hard to visualize. It's hard to kind of see, right? So to obtain the natural frequency is, you know, in the absence of most other forcings, that's the frequency that the object likes to vibrate, okay? But in order to get vibrations, you have to provide it some kind of stimulus. So the best way to do it is to perform what I call like the flick test. And so the flick test is that you take an object and you just flick it, right? And so for those of you in the class, you can kind of see, right? So I'm flicking this thing, and it's kind of hurting my finger a little bit, but you can see that as I'm flicking it, this projector thing is vibrating a little bit, right? So it doesn't last for very long because there's a lot of damping in the system. Right, my fingernail's hurting, but you can see that it does vibrate a little bit. Okay. So every physical system that's governed by second order ODE will have this natural frequency. Okay. And so the idea with resonance is that if you provide a forcing with a frequency that's oscillatory that matches the same frequency, that basically that natural frequency plus the forcing are always just going to keep adding together, and then resonance is going to occur. So practically speaking, you know, when you're designing structures or you're designing mechanical parts or you're designing circuits, you know, you always need to be aware of what the natural frequency of your structure is going to be. And if there's any kind of resonance risk or any kind of vibration risk associated with it. Okay? So for the mechanical engineers in the room, next year you're going to take course 431, which is vibrations. A lot of that course is focused on just this idea of resonance and natural frequency and kind of avoiding those things. Okay, any questions on resonance here? All right, so for the homework problem, homework 4 on homework 2, that homework problem kind of asks you some questions about resonance. So if you're designing a building, one thing that occurs in California specifically are earthquakes. So earthquakes is kind of a prime example of an oscillatory loading or an oscillating load, right? So when you're designing a building, you want to make sure that the natural frequencies of the building don't match the common frequencies that occur in earthquakes. Otherwise, your building is at risk of earthquake failure. Okay? Fun fact, our CS building here, so the one that's kind of right behind this classroom, that building is earthquake proof, or not earthquake proof, but it's earthquake certified. And so it's resistant, it's very resistant to earthquake loads. But ironically, the engineering building, which houses all the mechanical engineers and the civil engineers, that building is not earthquake certified. So if a big earthquake were to occur, the building, which has all the people that could design the building, would probably collapse and kill us all. So, yeah, not a good thought. I try not to spend too much time in my office. I'll say that. Okay. All right. So that's resonance. All right. So for the last 30 minutes of class today, let's move on to let's kind of shift gears almost completely. And let's talk about Laplace transforms. Okay. So like I mentioned at the beginning of class today, up until this point in the class, I think a lot of this has kind of been review, probably for a lot of you. Hopefully it's been a lot of review. It seems like it's been a lot of review, just looking at your guys' homeworks. But Laplace transforms, I think, is probably the first time that you're going to learn something that's completely new. Okay. Okay. So what are Laplace transforms? So a Laplace transform kind of belongs to this class of mathematical techniques called integral transforms. Okay. Okay. And so to perform a Laplace transform, you need to perform an integral. Okay. And the idea is to essentially perform a change of variables. Okay. So we're going to change the independent variable in our problems. We're going to change it from our usual suspects, which are space and time, into something kind of different. Okay. So in particular, for Laplace transforms, we're going to take a variable in the physical domain. So physical domain variables would be variables like x, which is space, or t, which is time. Okay. We're going to be working much more with time from this kind of point forward. Okay. So you're going to see a lot more differential equations in terms of t instead of in terms of x. Okay. And then we're going to transform it into what I call kind of the Laplace domain. Okay. And what is the variable for the Laplace domain? It's very straightforward. It's the first letter that you think of when you see Laplace, which is S. Right? Because S is totally a letter that is present in the word Laplace. I don't know why they chose S. It's even confusing because S looks like a 5, and that makes it even more confusing. But that's the variable that they chose for Laplace. Okay. So why would we do this? Why would we go through the trouble of transforming something that we work with probably for your entire time here as a student? Why would we go through the trouble to change it to a different variable? Okay. So the idea with Laplace transforms and with integral transforms in general, this is not the only integral transform we're going to go over in this class. We're going to also go over a Fourier transform as well. Okay. The idea with the Laplace transform is to basically make certain problems easier to solve, or to make some problems solvable that weren't solvable before. In particular, for Laplace transforms were designed to help us solve differential equations. Okay. So I kind of lied to you a little bit. So I told you we're leaving differential equations, but we're just coming right back to solving them. We're just solving them in a different way. Okay. So the benefit for Laplace transforms is that a Laplace transform will basically take your differential equation and basically transform it into an algebra problem. Now, of course, that depends on your feelings towards algebra. So some people will see that and be like, well, B, like algebra, that's great. It's better than, homogeneous solution, particular solution, algebra is something that you've probably done for a long time. But also some people are like algebra, like, oh man, algebra is kind of really tedious. And so, when I first taught this class, I said Laplace transforms make solving equations easier. But then I got a lot of complaints, and so I won't say that anymore. So I won't say I won't say it makes the problems easier. It's just an alternative way to solve these problems. Okay. And this actually affords us some benefits. Okay? Right. Because one of kind of the cumbersome ways to solve, or kind of one of the cumbersome aspects of solving differential equations, at least the way that we've been doing it, is there's lots of different steps, right? So lots of different phases to the solution. So think back to just what we just finished covering today. So, you have to solve for the homogeneous solution. You have to take a guess for the particular solution. You have to solve the particular solution. Then at the end, you have to plug in the initial conditions to solve for the full solution, right? So there's kind of lots of different steps, and each step is kind of disjointed from the other, okay? With Laplace transforms, it's you kind of solve for the entire problem in kind of one big kind of monolithic step. So that means initial conditions, boundary conditions are all kind of fully incorporated into the Laplace kind of framework. Okay. So in some ways, the framework itself is easier to remember because there's less steps to the whole process, right? There's just a lot of algebra that kind of goes up. But this is a benefit. So, you don't have to worry so much about forgetting a certain step. Okay. The other main benefit that we'll see is that we're going to be able to basically utilize different kinds of forcing functions or different kinds of non-homogeneous terms that we haven't been able to use before. And in particular, these non-homogeneous terms that we can use are actually quite common in engineering practice. Okay. And in particular, the two that we're going to be going over in this class are step functions and impulse functions. Okay. Which represent kind of two kind of very important kind of classes of functions in engineering systems. Okay. Okay, so that's kind of the game plan for probably the next 3 or 4 lectures. Is we're going to be going over Laplace transforms. It's going to take us a while to build up kind of the theory of Laplace, so we probably won't see differential equations for a while, maybe not until the end of lecture on Thursday. But this is kind of the ultimate goal is to introduce Laplace transforms as an alternative way to solve these differential equations, to allow us to do a few more things with them that we couldn't do with. Okay. All right. Any questions on this so far? Okay. So let me kind of lay out kind of the roadmap of how to solve an equation with Laplace. Okay. So solving an ODE with Laplace, first we're going to start with our differential equation. Okay. And so that usually includes some initial conditions as well. Okay. First thing we're going to do is we're going to perform a Laplace transform. And so what this is going to do is that instead of an ordinary differential equation, we now are going to have an algebra problem. Okay. Right. Again, I say algebra problem as if it's easier, but you know, some of you may feel differently. Depends on how you feel towards partial fraction decomposition. So hopefully that rings a bell. We're going to be doing a lot of that very soon. Okay. Once you have the algebra problem, you're going to perform algebra to find the solution. Okay. But the solution here is going to be in the Laplace domain. Okay. Right. But usually our solution in the Laplace domain is not that useful to us because you know it's hard to kind of visualize or kind of you know utilize this function, right? Usually we want to get our solution in terms of space or time, just so that we can kind of interpret it a bit easier. So once you have your solution in the Laplace domain, you have to perform the inverse Laplace transform. Right. So there is an inverse, so there's a way to kind of take it back. Okay. And then once we do that, we have our solution to our original ODE. Okay. And the physical domain. And then we're done. So that's how you would solve an equation with Laplace. You take an ODE, you take its Laplace transform, you solve it within the Laplace domain, then you take the inverse Laplace and transform it back into the physical. Okay. Okay, so that's kind of the goal for the next few lectures is to kind of, you know, fill out this kind of flow chart here and kind of know how to do every single step, just so that you can kind of start solving these problems. Okay. So that's great. So that all sounds good in theory, but let's actually start, you know, learning how to actually do it. So it all starts with the Laplace transform itself. Okay, so how do you compute the Laplace transform? So remember I said the Laplace transform essentially is a change of variables. So you're going to take whatever variable that your function was of before, whether it be x or t, and then transform it into s. Okay. Okay. So mathematically it looks like this. And so if you have some function f, okay. And so to take its Laplace transform, the way we denote it is we kind of put a fancy L around it. Okay. So this L here represents a Laplace transform. Okay. So you're going to see me use that terminology or that symbol, you know, quite a lot. Okay. And so the way that you do this is you take the integral from 0 to infinity of your function. Okay. And for now, I'll just pretend that, you know, this function is a function of t. Okay. So that is its physical domain variable. You're going to multiply this function by e to the minus s times t. And then you're going to integrate with respect to that physical variable. Okay. And so by performing this integral here, your physical variable t is going to be integrated out. And so essentially you're going to be plugging in for it And then it's going to be instead replaced by a function of s instead. Okay. All right, so let's do a couple of examples so that you can kind of see what this looks like. Okay. All right, so let's do the simplest case first. So let's do a constant function. So let's take the Laplace transform of just one. Okay. Okay, so we have integral from 0 to infinity of 1 multiplied by e to the minus st dt. Okay. So this is pretty straightforward. We just have an exponential function here. Okay. And so if we take the integral of this, we have integral of e to the minus st. So that's minus 1 over s, e to the minus st. Okay. Evaluated from 0 to infinity. Right. So doing these integrals is a little bit confusing because s is a variable, but when you're taking the forward Laplace transform, you're integrating with respect to t. And so you essentially treat s as if it were a constant. Okay. So that's why we have a minus 1 over s that comes out, even though we know that our new function is going to be in terms of s. Okay, so let's go ahead and plug in for t here. And so we have minus 1 over s. We plug in the integration bounds. We have no need for an arbitrary constant here because it's a definite integral because we have bounds. Okay. So you have e to the minus infinity minus e to the 0. Right. So we know e to the minus infinity approaches 0. So we can just eliminate this one. And e to the 0 here is just going to be 1. Right. And so we have minus 1 over s times minus 1. And so that means our Laplace transform of 1 is equal to 1 over s. Okay, so this is interesting. So a constant function in the physical domain is not a constant function in the s domain. So we actually get 1 over s. And so that's actually quite interesting in terms of how we're going to apply this. Right. But this is just a quick example of how to take the Laplace transform. I have a couple more for you, but this is kind of where we're starting. Any questions on this transform here? Okay, so let's do another one. Okay, so let's do the Laplace transform of e to the at. Where a here is just a constant. Okay, so let's go ahead and plug it into our transform formula. So we have integral from 0 to infinity of e to the at multiplied by e to the minus st dt. Okay. So since we have two exponential functions here, let's just combine them together into one. And so we have integral from 0 to infinity of e to the a minus s t dt. Minus, excuse me, or no minus. Okay, so let's integrate it. And so we integrate this, we get 1 over a minus s multiplied by e to the s minus a minus st. Okay. Evaluate this from 0 to infinity. Okay. So once again, we have 1 over a minus s multiplied by e to the infinity, minus infinity, excuse me, okay, minus e to the 0. So once again, we have e to the minus infinity, that is going to be equal to 0. And e to the 0 here is equal to 1. And so the Laplace transform of e to the at is equal to 1 over s minus a. Question in the chat. Well, we're not there yet. We're not at solving for particular solutions just yet. This is just kind of the warm up for me. All right, any questions on this example here? Okay, let's do one more together. Okay. So let's do the function f of t is equal to t. Okay, so just a linear function of t. Okay, so if we take the Laplace transform of t, that's equal to integral 0 to infinity t e to the minus st dt. Okay. Okay, so this one we're going to have to solve with integration by parts, and so we have t multiplied by an exponential. Okay. So we have u is equal to t, du is equal to dt, okay, dv is equal to e to the minus st, and v is equal to minus 1 over s, e to the minus st. Okay. Okay, so let's do this. So we have u times v, which is a minus t over s, e to the minus st, okay, minus integral of minus 1 over s, e to the minus st dt. Okay. Okay, so that second integral we can do. So we have minus t over s, e to the minus st, minus 1 over s squared, e to the minus st. Okay. And we're going to evaluate all this from t is equal to 0 to t is equal to infinity. Okay. So let's evaluate these bounds. Okay. And so let's evaluate the bound at t is equal to infinity first, since we have minus infinity over s, e to the minus infinity here, okay, minus 1 over s squared, e to the minus infinity. Okay. So on both terms here, we have an exponential to minus infinity, so that is going to approach 0. I know on the first term there we have an infinity over s, but an exponential term is going to approach 0 faster than the infinity is going to reach infinity. So both of these terms we can assume are 0. Okay. Minus, we have a minus, so we're going to evaluate everything at t is equal to 0 now. So we have a minus 0 over s, e to the 0, minus 1 over s squared, e to the 0. Okay. Okay. So that first term there, we have 0 over s times e to the 0. Even though, so e to the 0 is going to be 1, but we have 0 over s, that's just going to be 0. Okay. Then that second term there, we have e to the 0, which is going to be 1. Okay. And we have minus 1 over s squared. So we want our next function to be in terms of s, so we can just leave that. Okay. And so in the end, the Laplace transform of t is equal to 1 over s squared. All right, any questions on this example here? Okay. All right, so finding Laplace transforms of simple functions is, we just did 3 in like 10 minutes, and so it's fun to some degree, just because these problems are fast. But I have good news to break for you, is that typically when you're taking Laplace transforms of functions and you're using it in a practical way, you almost never use the integral form like this. And so I want to do this example just to kind of show you where these come from. But typically when you use Laplace transforms, you're going to use a table instead. So this table will be kind of the last thing that I show you for today. And then we'll pick it up from here on Thursday, and you can see how we take this, okay? So how to use the table. So the table basically just takes all these results that we just did, as well as for some other common functions, and it just tells you what the Laplace transform is, okay? So I'm going to write down the table here, or as many terms as I can in the next 3 minutes. But I have a nicer, more formatted version of this table on the Canvas site that you can download as well. Okay. And for the exam too, just because I know people will ask this, I will provide this Laplace table for you on the exam as well. Okay. So the table looks like this. So on one column, you have the function in the physical domain. And then in the other column, you're going to have its corresponding Laplace transform. Okay. Okay. So for example, we did the Laplace transform of the function 1. The Laplace transform for that is 1 over s. Okay. We also did the Laplace transform of t. The Laplace transform of that is 1 over s squared. Okay. We also have t squared. Okay. So t squared is 2 over s cubed. Okay. We can keep going. So for any polynomial, so any polynomial raised to a positive integer n, okay, the Laplace transform for that is n factorial divided by s raised to the n plus 1 power. Okay, so you can use this table here to come up with the Laplace transform of t cubed, t to the 4th power, t to the 5th power, t to the 6th power, right? You can use this table for that. Okay. Okay. Another important one to know that we just did, we have e to the at. The Laplace transform for this is 1 divided by s minus a. Right? That's actually going to be a really important one that we're going to use a lot when we're solving ODEs. Okay. Okay, I'll give you a few more. I'll finish this table next time, but just because we're kind of running out of time today. All right, another common one that you're going to find is cosine. Okay. So the Laplace transform of cosine omega t is s divided by s squared plus omega squared. Okay. Sine omega t, its Laplace transform is omega over s squared plus omega squared. Okay. And then let me give you the hyperbolic ones, and then we'll call it for today. Okay, so we have hyperbolic cosine, so cosh of omega t. Okay. The Laplace transform for this is s over s squared minus omega squared. And then hyperbolic sine, so sine h, okay, omega t. Laplace transform for this is omega divided by s squared minus omega squared. Okay. There's a couple more entries on the table, but we'll cross that bridge when we get there. So when we come back on Thursday, make sure you kind of write this down, or maybe download the one that's on Canvas. That one's formatted much nicer, and then we'll find out how to actually use these to solve differential equations. Okay. All right. So thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you on Thursday. Thanks, Joel.
Professor,
What's up?
I was just wondering if there's a specific reason why we use an exponential function, like to integrate the Laplace transformation.
That's just how the Laplace transform is defined.
Yeah.
So in our case, the differential equation has worked out pretty well, just because exponentials actually show up a lot in solutions to differential equations.
Yeah.
And the fact that the Laplace has an exponential actually synergizes really well with that.
Oh, okay, yeah.
So you'll see probably Thursday, Mike. Sweet, thank you.